Welcome to today's Explainer. Speaking as a researcher who spends literally every single day looking at the microscopic building blocks of life, I can tell you right now, we have just crossed a frontier we once thought was absolutely impossible. Seriously, if you step into my shoes for a second and imagine working in a modern neurology lab, you quickly realize we aren't just looking at flat tissue samples anymore. We are decoding an unimaginably dense universe. So today, I'm going to walk you through a step-by-step research discovery that fundamentally alters our entire understanding of human biology. We're exploring this monumental project from Harvard and Google, and we'll break it down logically. We'll start with the physical extraction of a minuscule sample, then move into the colossal digital conversion process, and finally look at the groundbreaking medical applications this unlocks for the future. So get ready, because the sheer scale of what we've discovered in the space almost completely invisible to the naked eye, well, it's going to shatter your perception of what physical matter can actually hold.
Let's start with a mystery number, 1.4. Right now, in the scientific community, this specific number is turning heads absolutely everywhere. But 1.4 what? Is it 1.4 million cells? Maybe $1.4 billion in funding? No. This number represents the unbelievable volume of digital data generated from just a microscopic speck of human brain tissue. And generating a number like this? It isn't just a scientific feat. It's a massive financial and structural reality. To process this specific amount of data, to literally map this much biology, requires a jaw-dropping financial investment. We're talking millions of dollars poured into enterprise-scale server arrays, massive computational costs, and entirely custom-built infrastructure. Honestly, for the non-experts looking at the business impact here, this signals a major shift. The tech industry and biological sciences are now permanently merged. Big tech companies aren't just providing search engines anymore. They are providing the foundational architecture required to decode human existence. It's creating an entirely new economy centered around biological data storage and analysis.
So the number is 1.4 petabytes, and to put that into perspective, a petabyte is a unit of digital data equal to 1 million gigabytes. Now, most of us are pretty used to gigabytes, right? Your smartphone probably has 128, maybe 256 gigabytes. But a single petabyte is 1 million of those. If we use an everyday storage analogy, 1 petabyte is roughly equivalent to storing over 300,000 high-definition movies. Think about that. If you sat down to watch all of those back-to-back without sleeping, it would take you over 60 years to get through the whole catalog. And the data we generated isn't just 1 petabyte, it's 1.4. Dealing with this kind of volume creates three major technological hurdles that researchers are facing right this second. First, physical storage limits. Housing this requires literal, physical warehouses just full of hard drives. Second, transfer bandwidth. You definitely cannot just email a petabyte. Transferring it takes specialized, incredibly high-speed fiber networks. And third, analysis rendering. Just navigating a 3D model this large requires advanced machine learning algorithms just to load the visual without completely crashing the computers.
Now there is a stark, almost unbelievable juxtaposition here. We have physical space pitted directly against digital size. We are talking about a single cubic millimeter of human brain tissue. To visualize that, think about the tip of a sharpened pencil. That is roughly 1 millimeter. As a scientist sitting at the bench, looking at a physical sample that small, you could easily accidentally sneeze and lose the entire thing. Yet that tiny little speck translates into more than 400,000 high-definition movies worth of data. So how can something so physically minuscule contain a digital reality so incredibly vast? Let me use a simple household analogy to explain this mapping complexity. Imagine trying to map out every single electrical wire, plumbing pipe, air duct, and fiber optic cable inside a massive skyscraper, and then taking that entire chaotic labyrinth and shrinking it down to the size of a single grain of sand. That is exactly what we're doing with the billions of neurons, synapses, and glial cells packed into this tiny fragment of biology.
Mapping the infinite. As researchers, we really don't use words like infinite lightly. We didn't call this project mapping a millimeter or mapping a small piece of tissue. We called it mapping the infinite because when you take that single millimeter and watch it unpacked into 1.4 petabytes of data, the sheer complexity feels, well, absolutely boundless. Every single connection, every branching dendrite, every tiny pathway in that sample is a literal world unto itself. But this isn't just some abstract scientific exercise. It has massive societal benefits for the general public. By creating a map of this crazy fidelity, we're building a public good, an open-source foundation that empowers researchers globally. It means a lab in Tokyo, a university in London, and a clinic in Boston can all explore the exact same microscopic terrain simultaneously. It proves that the human brain is the most densely packed, incredibly sophisticated information storage system in the known universe, and we're finally building the tools to actually read it.
Okay, let's break down the core facts of this scientific breakthrough, because it perfectly showcases the power of cross-disciplinary collaboration. This joint atlas project works so perfectly because Harvard brings the absolute pinnacle of medical sample preparation to the table, while Google provides the massive computational power required to process all that data. But let's ground this in reality for a second, and look at how this accelerates future neurological treatment pathways. Imagine a near-future hypothetical scenario where this data solves a specific health crisis. Picture an attending physician treating a patient with severe, drug-resistant epilepsy. Instead of using generalized treatments, the doctor accesses a petabyte-scale digital map of the patient's own neural pathways, pinpointing the exact microscopic cluster of misfiring synapses that's actually causing the seizures. Or imagine identifying the microscopic origin of Alzheimer's plaque formation years before a single symptom even appears. That is the real-world application here. We are actively transitioning medicine from educated guesswork into microscopic precision engineering.
Which brings us to the ultimate, staggering question. If just 1 millimeter holds 1.4 petabytes, what does the entire human brain hold? Let's test your understanding with a quick thought experiment. If just one pencil-tip-sized fragment equals 1.4 million gigabytes, how many zettabytes of data do you think it would take to map your entire mind, with its 86 billion neurons and trillions of connections? The math is so vast it honestly challenges our very comprehension of data itself. So to wrap up with a simple summary of our learning outcomes today, we've explored the step-by-step journey from the physical extraction of a 1 millimeter tissue sample to the colossal digital conversion yielding 1.4 petabytes, right through to the profound technological and medical advancements this brings to human health. We have successfully bridged the gap between microscopic biology and macroscopic digital infrastructure. Thank you so much for joining me on this incredible discovery today. Keep wondering, keep learning, and I'll see you next time as we continue to map the fascinating universe within us.